All right, this is Unit 7, Lesson 3. Today we kind of two topics. We're going to be solving exponential equations today, and then we'll be starting to talk about the properties of logarithms. We'll continue to talk about the properties of logarithms in the next lesson as well. So this is just like an introduction to that. All right, so I'm going to skip through this because we did it in class, but it doesn't really make so much sense for the video. All right, so solving exponential equations. I want to know, for what value of x is this equation true? In other words, what x value makes 3 to the x power equal to 50? When we're solving exponential equations, the strategy that we're going to be using is to take that exponential equation and actually convert it into a logarithmic equation. So over here on the side, I have the strategy. If you know that b raised to the happy power is equal to kelp, then that means the log base b of kelp is equal to happy. So those two equations are identical. They're just two different versions of the same equation. If we rewrite this as an exponential equation, we would have the equation log base 3, and it would be the log base 3 of 50 is equal to the power, which is x. So right away, we know the value of x. X is equal to log base 3 of 50. If you wanted an exact answer, that'll work. That's exact. If you wanted a decimal approximation, you'd have to figure out what log base 3 of 50 is. So I wanted to show you a way to have your calculator calculate something like a base 3. We talked before with the calculators about that the LOG button is base 10, and that the LN natural log button is base E. But if we want to know something that's base 3, we need a base 3 button. Well, the calculator doesn't have one, but if you hit math, there is a menu option that will allow you to change the base. So I usually scroll up. You could scroll down, but scrolling up is faster because it's down by the bottom. And it's right here where it says log base. So if you hit enter there, it allows you to put in whichever base you want. So this will be log base 3 of 50, and then we can get the answer to that. It's about 3.561. So this right here is the exact answer, and this is a decimal approximation of that value that we got from the calculator. So this was a really simple equation. We're going to look at some that are a little bit more complicated. Just have to think about your order of operations though, and they're not really any more difficult than the one we just did. Just maybe more steps. So if we want to solve this equation for x, we have 2 to the x minus 4 power is equal to 100. So if we rewrite that as a logarithm, it would be a log with base 2. Remember, whatever the base is, the base stays the same. So it'll be log base 2 of 100 is equal to the power, which is x minus 4. So again, the calculator can help us figure out what log base 2 of 100 is. We'll use that math button. Hold on, sorry. Math. And we'll scroll up to, whoops, oh, sorry. Scroll up to that log base. And we'll put in base 2 of 100. And we get 6.644. And that's equal to x minus 4. We want to know what x is, so our last step would just be to add 4 to both sides of our equation. So we end up with the equation 10.644 is equal to x. And again, that's a decimal approximation for the value of x. If we wanted an exact value, we would leave it like this and add 4. So exact value of this would be log base 2 of 100 plus 4. Uh, the only reason I'm talking about those exact values is that on the ACT they often don't go to decimal approximations. They often leave them in this form with the log. So I just want you to sort of be used to seeing that. But for my purposes, I want you to get that decimal value. All right, this next equation has 5 to the power x plus 2, and then we're adding 3, and that's equal to 25. So before you can convert this, before you write it in a logarithmic form, you need to have it as just a pure exponential. So we need to take care of this plus 3 very first. So we'll subtract 3 from both sides. And sorry if that looks like I was dividing. If we subtract 3 from both sides, we now have the equation 5 to the power x plus 2 is equal to 22. So if you have extra things happening to that exponential, then you need to take care of those first. So now we're ready to write it as a log. This will be a log with a base of 5. So log base 5 of 22 is equal to the power x plus 2. Again, if we wanted to get an exact value, we could just subtract the 2, but we're going to go ahead and get the decimal here. So we have log base 5 of 22. So we find that log base. Oh, whoops, sorry, I typed 2. Log base 5 of 22. And we get 1.921. And that's equal to x plus 2. So to finish solving for x, we just need to subtract 2 from both sides of our equation. So we'll subtract 2 to get negative 0.079. And again, that's a decimal approximation. All right, let's just look at 2 more. These ones are both with a base of e. So we have 40 times e to the 0.6x power is equal to 240. For this first equation, we have just a base of e for the exponential. The 40 is not being raised to that power. So this 40 is something that we need to take care of first. It is a coefficient to the e to the power 0.6x. So we want to go ahead and divide by 40 first. So we get e to the 0.6x is equal to 6. Now we're ready to write that as a log equation. And so it's a log with a base of e, but maybe you recall that that's the same as a natural log. So usually I don't write log with base e. Usually I just write that ln symbol for a log with base e. But it's not wrong if you do. But it is going to be a natural log. So it's a log with base e. A natural log of 6 is equal to the power 0.6x. So in the calculator, this time you don't have to use that base button. You can just directly type in the natural log of 6. Now, if you did go ahead and use that log base button and put in a base e, it will give you exactly the same answer. So it's not going to be incorrect. So we get 1.792. And that's equal to 0.6x. So then our last step would just be to go ahead and divide both sides of the equation by 0.6. So we get 2.98. Let me write, sorry. .987. All right, this last one, we need to get that exponential by itself. So our first step is going to be to subtract 1. So we have the equation e to the negative x is equal to 9. So if we rewrite that as a log equation, we have a natural log, because it's base e, of 9 is equal to negative x. So you can think of this next step as dividing by -1 if you want, or timesing by -1. This would just be the negative natural log of 9 is equal to x. So this would be an exact answer. If you typed that into your calculator, the negative natural log of 9 is negative 2.197. So that would be our x value. All right, so that is solving exponential equations. The reason they have you solve exponential equations right now is because I wanted to give a purpose to logs. One of the reasons that we need logs and use logs is so that we have a method of solving an exponential equation beyond just guess and check. So that was solving exponential equations. We're now going to kind of switch gears and again, we'll solve log equations later, but today we're focused on the exponentials. We're going to switch gears now and study the properties of logs because we need a few more tools for dealing with logarithms before we finish out our unit and before we start solving log equations. So we'll be talking about the properties of logs. So the first property of logs we're going to talk about is called the product property. So the product property tells us that the log of u plus the log of v, so if I have two logs that are being added together and they have the same base, it's exactly equal to the log base b of uv times together. And that's kind of crazy. It's not something that you're used to. It's a property of logs only. So it's called a product property because when we add two logs together, it's equal to the log of the product. We use this property in a couple of ways. Sometimes we have two logs being added and we want to do something that's called condensing. So we can take those two logs and condense them into one logarithm. But sometimes we actually want to do the opposite. Sometimes we have a log of a product and we want to do something called expanding it. So we kind of go both ways just depending on what our goals are. It's really important though that you understand that the base, whatever the base is, it stays the same and they do have to have the same base. If they're different bases, you cannot use this property. So we're going to look at both some condensing and some expanding, and we're going to start with condensing. So if I have the log base 2 of x and I'm adding the log base 2 of y, that's exactly the same as log base 2 of xy. So anytime we have two logs being added together, it's the log of the product. So in this case, with log base 6 of 12 adding to log base 6 of 3, it's going to be a log base 6, and if I multiply those two things together, the 12 and the 3, it's going to be a 36, log base 6 of 36. And hey, wait a minute, log base 6 of 36, you should maybe be able to think through that one. Remember, logs are asking what power of 6 is 36, so this one simplifies to the number 2. So log base 6 of 12 plus log base 6 of 3 is equal to 2. All right, the next one, the natural log of x plus the natural log of 5. We can use the product here, the natural log of, and usually we would write that 5 first as a coefficient, so it's the natural log of 5x. This next one has the log base 10 of 6 and the log base e of x. Log base 10 and log base e are not the same base, so this one would just have to remain as is. You can't combine them. They are different bases. All right, log base 10 of 2 plus the log base 10 of 7 plus the log base 10 of x. It works if you have 3 logs being added together as well. This would be the log base 10 of 14x if I times those things together, 2 times 7 times x. So that's condensing. Condensing is like a way of combining logs into one single log. Now we're going to expand going the other direction. If I have the log of x times y, I can expand that into the sum of 2 logs. It's the log of x plus the log of y. And if I wanted to expand the natural log of 9y, it would be the natural log of 9 plus the natural log of y. Log base 2 of 8x, we could expand to the log base 2 of 8 plus the log base 2 of x. Now this one, if you notice, you might have thought, hey, I know the log base 2 of 8. Or maybe you didn't think that, but it's okay if you didn't. But log base 2 of 8 is a whole number. Log base 2 of 8 is asking you what power of 2 is 8, and 2 is the third power of 8. So we could simplify this to 3 plus the log base 2 of x. All right, the last one of these, we have the natural log of 7e. So we could expand that to the natural log of 7 plus the natural log of e. And hey, the natural log of e, this is a log with a base of e of e. What power of e is e? This is 1. So this is the same as the natural log of 7 plus 1. Be careful here. This is not equal to the natural log of 8. You can't combine the 7 and the 1. If you want to think about it with parentheses around that 7, you can. But the 7 is the argument of the log, and then 1 is being added. Sometimes because of this like ambiguity of how it kind of looks a little confusing, sometimes that's why they'll write the whole number first and say 1 plus the natural log of 7, because then it doesn't look quite as, people really want to combine that into an 8 when it's written this way. So sometimes writing it this way can help prevent that problem. Either way is fine, but just make sure you don't combine it into an 8. All right, so that was the product property. We have another property called the quotient property. Quotient property of logs tells me that if I have a log of u and I'm subtracting a log of v, it's the same as the log of u divided by v. So it's called the quotient property. If we have those two logs being subtracted from one another and we want to condense it into one log, we can do that. Or we can go the other way. If we have the log of a quotient, we can expand it into a subtraction of logs. Just like before, it's really important that you have the same base if you're applying this property. So we're going to practice both condensing and expanding these expressions. So we have the log base 2 of x and we're subtracting the log base 2 of y. So this would be the same as log base 2 of x over y. For the second one down, and the order there does matter. It's divided by y because we're subtracting the log of y. For the second one, we have log base 6 of 72 subtract log base 6 of 2. That's going to be a log with a base of 6 of 72 over 2. Now 72 over 2, or 72 divided by 2, is the same as 36. So that's log base 6 of 36. And log base 6 of 36 is just asking what power of 6 is 36. This one is equal to 2. So log base 6 of 72 subtract log base 6 of 2 is exactly equal to 2. Okay, the natural log of 5 subtract the natural log of x. That would be the natural log of 5 over x. And this last one, the log of 14x subtract the log of 2 would be the log of 14x over 2. So we could say that that's the log of 7x, because you can go ahead and divide that 2 out. Okay, now we're going to practice expanding. Log of x divided by y is the same as the log of x. Subtract the log of y. The natural log of 9 over x is equal to the natural log of 9 minus the natural log of x, which is not the same as the next one. The natural log of x over 9 would be the natural log of x subtract the natural log of 9. So be careful about the order. It does matter. You subtract the log of the denominator. Okay, the last one on this list, the log base 5 of 25 over x would be log base 5 of 25 subtract log base 5 of x. Log base 5 of 25, though, that's one we should be sort of familiar with. Log base 5 of 25 is exactly equal to 2. 5 squared is 25. So our final answer would be 2 minus log base 5 of x. Okay, we have one final property. It's called the power property of logs. So if we have c times the log base b of a, that's exactly the same as the log base b of a to the c power. So this is kind of a weird one. It's like you can bring that coefficient up as a power. So just like the other rules, we can do something called condensing. That's when you bring that power up. Or we can do something called expanding, which is when we bring the powers down. And again, with this property, same as with the others, you have to have, or that base stays the same. So we're going to use the power property here. If I have 5 times the log base 2 of x, that's exactly equal to the log base 2 of x to the 5th power. It's like bringing that 5 up as a power. Negative log 4, it's kind of like a negative 1 if you want to think of it that way. So this would be the log of 4 to the negative 1 power. And sometimes we don't like to have those negative powers, so we could write this as the log of 1/4. So the negative log of 4 is exactly the same as the log of 1/4. Again, if you're wondering where that came from, it's this rule of exponents. A negative exponent means that I can move that to the denominator with a positive exponent. All right, the next one, 7 times the natural log of y would be the natural log of y to the, sorry, my brain started writing a 4. The natural log of y to the 7th power. And 1/3 the log of x is the same thing as the log of x to the 1/3 power. Another way you could write that if you want is it's the log of the cube root of x. Either of those is fine. You don't have to write it as a cube root. I just wanted to remind you of that. Expanding means you're bringing the powers down. So we would take that cube and bring it as a coefficient. So this would be 3 times the log of x. Here we could bring that power down 3 times the natural log of 5. We could bring this power down. It would be 5 times the natural log of e. Natural log of e, remember that the natural log is base e, so this is e, the natural log of e is the same as 1. So this is the same as 5 times 1, which is just 5. And then this last one, log base 5 of x to the negative 2, we can bring that negative 2 power down and say that this is the same as the log, negative 2 times the log base 5 of x. All right, so those are our 3 properties. So what I want to do is actually just do some mixed practice together using these properties. So we're going to be both condensing and expanding. And remember that the base stays the same. So we want to express all of these as a single logarithm. So it's asking us to condense each of these expressions. So that first one is addition. So when we condense that, we're going to use the addition rule. So this will be the log base 2 of 5x. The next problem has a power. It has a coefficient, so we're going to use the power rule, and we're going to condense that 5 as a power. So this is going to be the log base 2 of x to the 5th power. The next one has subtraction. So we're going to use our subtraction rule property. So if we rewrite that, it's going to be the log base 2 of 5 over x. So I purposefully on that row used all 5s and x's so you could kind of see the difference between those three properties. Next row down, natural log of y minus the natural log of 7. We're going to use our subtraction rule. So it's going to be the natural log of y over 7. Sometimes with fractions, people like parentheses. I don't really care. Either way is fine. Next one is the natural log of 7 minus the natural log of y. That would be the natural log of 7 over y. So be careful on the order with those subtraction ones. 1/3 of the log of b would be log base, it's base 10 of b to the 1/3, which if you want, you can write that as a cube root, whichever one you like. Log base 3 of a plus log base 3 of c, we're going to use our addition rule. So this will be the log base 3 of ac. Log base 3, log x plus log y plus log z, we can condense all of those together. This will be the log of x, y, z. We'll just times that x, y, and z together. And the last one is asking us to condense using the power rule, so we'll bring that -2 up as a power, the natural log of x to the -2, or the natural log of 1 over x squared. All right, so that's condensing all mixed together. Let's do some expansion all mixed together. So as you're looking at each one, you need to decide which rule to use. So this first one has a power, so we're going to use the power rule. We would say that this is the same as the log base, log base sometimes just pops out of my mouth, as 6 times the log of x. And again, on this first row, I used all x's and 6's so that you would have to really think about which rule you're using. This second one has a product, so we are going to use the product rule. So as we expand this, it would be the log of 6 plus the log of x. The next one is a quotient. So we're going to use the quotient rule. So as we can expand this one, it will be the log of x minus the log of 6. Make sure you're paying attention to the order there. The denominator is the log that's being subtracted. The natural log of 3x is a product. 3x is a product, so we would expand this to the natural log of 3 plus the natural log of x. This next one is a quotient. We're going to use that quotient rule. So we're going to expand it using subtraction. It's going to be the log base 3 of x minus the log base 3 of 3. And log base 3 of 3, the power of 3 that's equal to 3 is 1. So this is the log base 3 of x subtract 1. Please note that it's this, the log base 3 of x, and then subtract 1. The -1 is not in the log. Okay, next one over is another quotient. This would be the log base 2 of 4 minus the log base 2 of 7. And I've kind of mixed in here quite a few of these that you have to actually think about and simplify a little bit more. So the log base 2 of 4 is exactly equal to 2. So this would be 2 minus the log base 2 of 7. This next one down has a power. We're going to bring that power down as a coefficient. So this is 4 times the natural log of y. This one, the log of the square root of x, remember that that square root can be written as a half power. So we would say that this is 1/2 the log of x. Sometimes people will write that as the log of x over 2. Either of those is fine. And then this last one, if we're expanding it, it's x times y times z inside that log. So we can expand that into the log base 9 of x plus the log base 9 of y plus the log base 9 of z. So I know these rules, sometimes they're a little bit weird at first. We'll continue working with them in the next lesson, and so you'll get lots more practice with them and you'll get the hang of them. So that is it for today, solving exponential equations and the properties of logarithms. Thanks.